absorbing chains. Okay, so it's been, for you it's probably another day. For me I just pressed the button again. So it's been 10 seconds since my previous lecture. Okay, so I remind you what we're looking at. We're looking at a continuous mating process in which every single time we pick one individual at random and we mate it with a dominant individual. Okay. And what I was just explaining in the previous video is that this is what we call an absorbing chain, because once you get to that endpoint, capital G, whatever happens, the next time you will still be capital G. Okay. And so you have been what we call absorbed into this state, and you can never leave it again. And as I was pointing out in the end of a previous video, these are also very, very important types of Markov chains. So regular Markov chains, they have the property, remember that's one important property that I sort of didn't emphasize too much, but that the limit, the W that we get as a limit is a positive vector. Okay, so this is an important characteristic of regular Markov chains. The probability distribution that we get at equilibrium, so in the long term, when we have converged, it's positive. In this case, as you can guess, this is not going to be the case because, well, most of the time I'm going to end up here. And actually, not most of the time, every single time I'll end up here, eventually. Okay? But what's going to be nice is I am going to be able to find ways of quantifying how long on average it will take for me to make my way into there. Okay? So, to give a definition, we say that a state, Si, in a Markov chain is absorbing if whenever it occurs on one generation of the experiment, whatever experiment you're running, it occurs every single time after that. Okay? So, what that means is that the probability that I go from I to I is 1. And the probability that I leave I for another j that is not I is 0. Okay. And okay, so it can be a bit more complicated than this. I mean, we can have sets of states that are absorbing, but here we're working on the case where we have only absorbing states, not absorbing sets. So in an absorbing state, this is the definition. And we can have several. I'll show you, I think I've removed it, but I don't know. I'll see. I can't remember if I removed it or not. But there are some very interesting chains with several absorbing states. If a Markov chain has at least one absorbing state, then we say it's absorbing. It's an absorbing Markov chain. Okay. When you have an absorbing state chain, so this chain here is absorbing. Okay, the probability of going from 1 to anything else than 1 is 0. And when I have an absorbing Markov chain, a state that is not absorbing is transient. So those two states here are transient. And I mean, why they're called transient should be quite obvious in terms of what we've said. Essentially, you're going to transit through them for some time until you reach an absorbing state. Now, yes, so I had not removed that example. So suppose I have an absorbing chain that takes this form. So this, forget genetics, this is a generic example. I have 4 states. I can go that way and I'll end up in 1. So this would have probability 1, of course. This one I don't know. There's like the probability of moving back and forth between 2 and 3 is something. I could be looping back and forth here. It doesn't have to. Okay. The same here. This one, on the other hand, is also going that way. And once I'm here, I keep on looping here. So here I have two absorbing states instead of just one, like in the genetic example before. And there's a bunch of interesting questions that I can ask about a chain like this one, or an absorbing chain in general. First one is, does the process eventually reach an absorbing state? Okay, so I have a random process. I start my random process somewhere in some state. Do I eventually reach an absorbing state? The second question that I may ask is, what is the average number of steps spent in a given transient state? So in this chain, the transient states are 2 and 3. Okay, how long? Number of steps is like a measure of time. Okay, so how long do I stay in one of those transient states if I start in one of the transient states? Because of course, if I start in an absorbing state, I remain there for all times. So that sort of closes the question. But if I stay here, how long am I going to stay here before I get absorbed? Okay. And actually, that's like a similar question. How many steps, so again, on average, how long am I going to walk in a chain like this before I am absorbed? And finally, what's the probability that I'm going to be absorbed in one of the two absorbing states if I have more than one? Okay, and that depends where I'm going to start. So to answer these questions, well, the first question is first very simple. Well, it's not a simple problem, but it is, the answer to it is quite simple. So, does the process eventually reach an absorbing state? The answer to that is given by this theorem here. If I have an absorbing Markov chain, the probability of reaching an absorbing state, I don't know which one, but reaching an absorbing state, the probability is 1. So in something like this, whatever happens, and okay, you can imagine that, for example, and this is going to be what we call a random walk, you could imagine that I have, instead of having just 2 and 3 here, I have an enormous number of such states that are like this, where I can move left or right or stay here, and I'm going to have a whole chain of that. And there's going to be millions, perhaps, okay? I start in the middle. I have, like, I can go one way or go another way, etc. It may take me a long time, but with probability 1, I am going to reach one of the endpoints. Again, it doesn't say how long it's going to take me, that result, but it is going to eventually happen. Okay. For the other questions, we look at the matrix in what we call the standard form. And the standard form should remind you of what happened when I was talking about reducible matrices, because this is exactly what this means. A Markov chain is absorbing if the graph is not strongly connected. This means that the associated transition matrix and the associated graph, so the associated transition matrix is reducible. So I can write it in block triangular form. So the way we write it is, if you remember in the definition of the irreducible matrix, we did it using the other form. So we wrote the matrix as something, a non-zero block here, a non-zero block here, and a 0 here. It doesn't matter. Okay, it's not important what they really what way you write it. This is just the way it's done in this presentation of the results that I'm giving you. Okay. So if I have k absorbing states, r minus k, so there's r, I'm still thinking of r as being the number of states. Out of those states, I have k that are absorbing and r minus k that are transient. Then I can write my matrix. I know that I can write my matrix in this form. So I'm going to have an identity matrix here on the top left, because this corresponds to the part of the matrix that says if I'm in a transient, in an absorbing state, then I have only loops. Okay. So let me illustrate this with the chain I was showing you before, because the genetic one is going to be a little simple for this, because it's only got one absorbing. The aim was not to do a loop around two, but so remember that this is happening this way. To make things simple, let me just say that it's like this. So let's say that here I have a probability 1/2 of going there, 1/2 of moving there, 1/2 and 1/2. And this is probability 1, and this is probability 1. Okay. If I look at the transition matrix for this graph, what do I have? So from 1 I can go to 1 and nowhere else. Okay, this is P. From 1 I can go to 1 and nowhere else. From 2 I can go to 1 with probability 1/2, or I can go to 3 with probability 1/2. From I cannot go to 4. From 3 I can go to 2 with probability 1/2, or to 4 with probability 1/2. And finally, from 4 again, I can only go to 4. Okay, so that's my transition matrix. It is not in standard form, but you can guess what's going to happen to make it into standard form. What do I need to do? I need to create a block of zeros in here, or I mean, let's start with making this ik here. So what I need to do in order to do this, I need to reorder my states. So here, my states, I'm just going to write their names here. This is 1, 2, 3, 4, 1, 2, 3, 4. So what I need to do here to get this form, I need to first list the absorbing states. So instead of doing this, I'm going to write that P prime, okay, it's not the same matrix as before, but through some transformations, I get equivalence. We say the matrices are similar. What I need to do is I need to list my states as follows. I need to do 1, 4, and let's say 3 and 2. 2 and 3. Let's keep the order simple as much as we can. 2 and 3. So in weird noise. In rows, I need the same order. Okay, and so what I want is the matrix that fits in here. So I take my probabilities and I write them, but now it's in this order. So from 1, simple. From 1, I can only go to 1. From 4, I can only go to 4. But 4 is now here. Okay, it's 4 to 4. So this is 1 here. And then from 4, I said I can only go to 4. From 2, can I go to 1? Yes, with probability 1/2. From 2, can I go to 4? No. From 2, can I go to 2? No. And from 2, can I go to 3? Yes, with a probability 1/2. And finally, from 3, I cannot go to 1. I cannot, from 3, yes, sorry, I cannot, yes, I can go to 4, 3. From 3, can I go to 2? Yes, with probability 1/2. And I cannot go to 3. And this is that form, standard form of the matrix. I make those blocks. Okay, this is I2, a 2 by 2 identity matrix. This is a block of zeros, as we were expecting. This here is, and see, I have the explanation here. This is going from transient states into absorbing states. So these are the probabilities that I'm going from those transient states 2 and 3 into absorbing states 1 and 4. And I could have a more complex graph, but in any case, I would end up with something here. It could also be 0, okay? But in practice, that's one of those matrices, and that's the one we call R. And finally, here we have the matrix Q, and that matrix Q describes how we are moving from transient states into transient states. Okay? So, of course, I'm going to come back with the genetics example later, but this is how you would do it for it's called a random walk. When you have taken your decomposition of your matrix in standard form, you can then do some computations, and the result of these computations is going to give you the answer to the other questions we asked. Remember, we had 4 questions. The first one we answered already. We're always absorbed. The other questions we had concerned the number of steps, etc. So what we do is we create first a remark, that matrix identity of whatever remains, so the matrix that has the same size as matrix Q here, identity minus this is an invertible matrix, always, due to the way we construct this matrix in standard form. So that matrix is invertible. The inverse of I minus Q is what we call the fundamental matrix of the Markov chain. Then we also create Ti, which is going to be the sum of the entries. So this is going to be a vector, okay? And that vector is going to have, for the ith component, the sum of the entries on the ith row of this fundamental matrix. And finally, we are going to create the matrix B by taking the product of n, okay, so that fundamental matrix, times this term here. Okay, so once you have your matrix in standard form, you can go ahead and compute these things. And the reason why you compute these things is as follows. They answer the questions we had. So from the fundamental matrix, the ij entry in your fundamental matrix is going to be the average number of time the process is in the jth transient state if it starts in the ith transient state. Okay, so if you look back to this example, suppose I start here, and of course the indices, I should point out, the indices are relative to the smaller matrices. Okay, so we have, in this case, we have 2 transient states, and so n will be a 2 by 2 matrix, and so n1 would be the first transient state, and n2 would be the second transient state. Okay, the indices are relative to the type of states and the index of the type of states in the overall distribution of states. So Nij is giving you the number of times you're in the jth transient state if you start in the ith transient state. The vector Ti, the ith component there, is going to be the average number of steps before you enter an absorbing state if you've started in the ith transient state. So if you go back to this guy, suppose I start in the first transient state, T1 is going to tell me how many times on average, okay, it's a stochastic thing, how many times on average will I be here until I enter a transient state. And Bij sorry, until I enter an absorbing state, of course. Bij sort of more qualifies this. It gives me the probability of entering the jth absorbing state if I started in the ith transient state. Okay, so for instance, B12 would give me here the probability of being absorbed here, given that I've started here. So let's go back to the genetic example. It turns out that when you look at this matrix, it's already in the proper form. There's one absorbing state, okay, only. So that's the genetic example, not the random walk that I was talking about. So the genetic example has one absorbing state here. This is the vector that describes how I can go from, in this case it's a vector, it could be a matrix, how I go from transient states into this absorbing state. And this is the matrix that indicates how I move about the transient states. And the remaining here is a block of zeros, okay? So this is I1, so just 1. This is R here, and Q is the 2 by 2 matrix here. And we can compute different quantities. So if we compute I2 minus Q, because Q is a 2 by 2 matrix, okay, here. If I compute I2 minus Q, I get this. So the fundamental matrix is just the inverse of this matrix, which here is trivial to compute. T is simply that fundamental matrix, the row sums of that fundamental matrix, which I get by simply multiplying by the column vector of ones. And B is n times R, so it gives me this vector here. It could be a matrix, okay? But in this particular case, we've only got one absorbing state, so things sort of boil down to something simple. And I've taken those things that we just computed and put them back in terms of what it is that we read in them. So for instance, this matrix here, the fundamental matrix, tells us here, for instance, how the average number of times the process is in the jth transient state. So let's say that we go down. Let's say first transient state. We're on average going to be twice there if I start in the, this is first column. So in the first transient state, if I've started on the second transient state, the second being, remember, it's the other one. And here, this is a simpler one. How many times on average, in this case, it's not an average, well, it's absolute. Remember that if we start little g, so recessive, then automatically the next step, we will be in hybrid. So that means on average, I am going to spend 1 time unit in the recessive before I move into the absorbent, the other into the hybrid. And the same way, Ti is this, and etc.